Now for the second of our two lectures, looking into deep space, galaxies. As we said last time, until we realized other galaxies were out there, it was thought that the Milky Way was the entire universe. Other galaxies are just so distant that it was impossible to really tell what they were. They just appeared to be fuzzy blobs, and they were called nebulae, for lack of a better word. But nobody really knew what they were for a very long time. Without knowing what they were, efforts were made to catalog them nonetheless. Messier and Herschel both cataloged, among other things, these faint nebulae and other objects. Nebulae in quotes, that is. We now know that many of these objects turn out to be galaxies. At this point, we have enough advanced technology that we're able to map out an even more significant number of galaxies. And so to the right here, you see an example of such a map. What's a little bit puzzling is this region near what looks to be the equator of this map, where you see very few galaxies. It's very sparsely populated there, and it became known as what's called the zone of avoidance. And astronomers were very confused as to why it was along this band we didn't see as many galaxies. But then, when you think about our position in the cosmos, we are part of a galaxy. And when you account for all the dust and gas and other stars that block our view, then it sort of makes sense how you're not going to see these faint galaxies behind all of those obstructions. Therefore, most of the galaxies we see are to our galactic North Pole and our galactic South Pole and some regions in between, but not near our galactic equator, so to speak, because that is where the most obstruction takes place. So the first attempts to measure the distances of other galaxies used Cepheid variables, and as we learned when we were studying stars, these kind of stars vary their brightness in a very predictable way. And so we know that specifically their luminosity is proportional to their period. So if we can measure their period and compare how dim they are to how luminous they ought to be, then we can determine exactly how far they must be away given how dim they are. So when we talked about Cepheids before, we mentioned them as being a standard candle. Standard candles are anything that we can use as a way to pinpoint a distance measurement in space. And so Cepheid variables were used to measure the distance to some nearby galaxies. As you might imagine, it would be difficult to see Cepheid variable stars in very distant galaxies because they are so dim compared to other stars galaxies are. So it's very difficult to make out any kind of individual star. So when you go farther out, we would have to rely on something else. And the Cepheids are used to calibrate the distances, but then, we were able to deduce some phenomenon that Hubble found, which was that the farther away a galaxy appears to be, the more redshifted its spectrum is. And so that implies a Doppler shift is taking place. In other words, all the galaxies are receding away from one another, or equivalently, the space in the universe is expanding. In fact, this turned out to be such a beautifully simple relation that Hubble could plot it right here as a line, which became known as Hubble's law. And so in algebra class, you may have learned y equals mx plus b is the equation for a line, excuse me, where b is the intercept. So if b occurs at 0, then it would just be y equals mx, m being the slope, and then you have your x and y coordinate. So Hubble's law is just the same kind of thing. It's a line. It's just instead of y, we have recessional velocity along the y-axis or the vertical axis. So y is now v. And instead of x, we have d for distance in megaparsecs. And so then h, the Hubble constant, is simply the slope of this line. So there are different types of galaxies as well. And here are some pictures to go along with as we go talk about the different types of galaxies. Spiral galaxies consist of spiral arms and a central bulge, and we call these type S galaxies. We may at first think that this is where the Milky Way belongs, but it's not quite right. This is a similar idea to how the Milky Way looks, but there's actually a subtype of spiral galaxies we'll look at in a moment that the Milky Way belongs to. In any case, do think of spiral arms and a central bulge when you think of spiral galaxies. Elliptical galaxies are, as the name implies, elliptical in shape or oval in shape. They exhibit no spiral arms, however, and they're fairly featureless. These are dubbed type E. Irregular galaxies are kind of a catch-all where they're sort of miscellaneous in shape. They're not really oval and not really spiral. They're just sort of patchy or irregular, and so those are called type IRR. Now here is the type of galaxy the Milky Way belongs to. These are the barred spirals. And barred spirals are basically similar to the spiral galaxies in that they do have spiral arms, but the arms kind of come out at the end of bars that are near the central bulge. So, I mean, in words, that's a little bit difficult to describe, but if you see the pictures here, then maybe that gives you an idea of what we're saying. And so these galaxies are called SB type. And again, this is the type of galaxy that the Milky Way belongs to. Then there are the S0 galaxies, which just look like the shape of a disk, but they don't really have any spiral arms. So the difference between this and an elliptical may be a little bit difficult to ascertain in your mind, but so, you know, a disk doesn't have very much thickness to it, so elliptical, think more of like an egg that may be a little bit thicker in size or shape, I mean. But basically the S0 galaxies look like what you would expect a spiral galaxy to look like if you took away the spiral arms. So all of these different types can be plotted in a diagram to help us organize the various types. And each one of the types can be subdivided further. So ellipticals, for example, range from E0 to E7. So this reminds us perhaps of spectral classes when we're talking about stars and how we say, well, there's the O, B, A, F, G, K, M stars, but there's also subgroups within those. For example, G5 is our sun. So we do a similar thing with these galaxies, and the number indicates something about the shape. So for elliptical, the more squished or oval you are, then the higher your number. The closer to a circle or a sphere, I should say, you are, then the lower your number. And then the spirals, the subcategories indicate something about how tightly wound the spiral arms are, and you know, similarly with the barred spirals. So plotting these, putting this all together, you can create a diagram that shows the different types of galaxies pictorially. And so when you do that, what you end up with is something that looks like a tuning fork. I don't know how many of you have actually played with tuning forks, but you know, it's got this central axis and then the two prongs coming off of it. You could also think of it as like, you know, a marshmallow or a hot dog fork for going camping. Anyhow, so on the left-hand side of this, you have your ellipticals, and you see that what's depicted here as the number increases, it looks a little bit more squished until you get to the SO, which remember were the disc without the spiral arms. And so then from there, you could branch off one of two ways. You could either branch off into the spiral regime, or you could branch off into the barred spiral regime. And the differences in how tightly wound those spirals arms are pictured here as well. And then the irregulars are kind of off in their own little, like I said, miscellaneous category. So we may wonder then, okay, well, before we get to that, couple other things to mention. Just like there are dwarf stars, there are also dwarf galaxies. And although don't take that comparison too literally, dwarf galaxies are not similar to dwarf stars in that they are not the corpse of a burned out galaxy. They're just dwarf in the sense that they are small. So they're difficult to see because of the fact that they're very, very faint. And other differences, besides the obvious, the shape, there are other differences that we notice in the different types of galaxies. We notice that the ellipticals consist of a lot of older stars, whereas the spirals in general have both older and younger stars. And the irregular, they have many hot young stars. And if you remember from the very beginning of the semester, I showed a similar image like this where, well, it was the full image rather than this just little part of it. When the Hubble telescope took a long exposure of deep, deep into space, it just allowed the shutter to be open and get as many photons as could come by from distant galaxies. And we were able to look back, very far back in time, and you see not only the variety of the colors of the galaxies, but the shapes, and also just randomly their orientation to us is a little bit different. Sometimes we're looking at them face on, sometimes edge on, and sometimes somewhere in between. And so we talked last time a little bit about galactic collisions, and so this is really the key to understanding why we have so many different types of galaxies. Because of this galactic interaction, you end up with various shapes. So as I mentioned last time, the galaxies may gravitationally come close enough to interact with one another and warp the way they are shaped. And again, no stars will collide in this process. However, we could think of time going by as starting out with all of these pretty galaxies that are very regular in shape and disk-like in shape. And then after time goes on, maybe some of them start drifting closer to one another and interacting, and then you end up with not just your disk galaxies, but then you end up with some of those elliptical galaxies as well, and they're kind of like the debris that results from these collisions. So that would make sense too, because we notice that with these elliptical galaxies you have more older stars. So they've been around longer to encounter having more chance to encounter a collision. And then also during that collision, stars are redistributed, and so maybe some of them are flung out into intergalactic space even. So here's an image of two interacting galaxies, and you see how they're just warping the shape of one another. And you yourself can participate in categorizing some of these galaxies by eye. There's a project called the Galaxy Zoo. I believe it's just galaxyzoo.com, but you can Google it to be sure. But there are just so many of these galaxies, and they're just impossible for computers to efficiently categorize them. And so this project actually uses human volunteers to, I think you do like a tutorial, and then you figure out, then you can start looking at the data and looking at the pictures and figuring out which galaxies belong to which categories. And so it's an interesting way to participate in a scientific project that will help further our understanding of galaxies and their classifications. So then zooming out even farther and getting back to some things we discussed at the beginning of the semester, we talked about how galaxies aren't just regularly distributed, but they sort of cluster. And so we talked about our own galactic neighborhood, and this is called the local group, which consists of mainly the Milky Way and the small and large Magellanic Clouds, the Andromeda Galaxy, and some other dwarf galaxies as well. And so the small and large Magellanic Cloud are basically satellite galaxies to our own Milky Way. You could think of them as moons, to how like we have the moon for our Earth. They're satellite galaxies for some larger galaxies. And so this picture here isn't actually obviously of the Milky Way, because we can't leave the galaxy to take it. But this is a picture, the main image is of Andromeda Galaxy, and you see that it also has satellite galaxies. So, and galaxies tend to cluster. Some of them cluster in larger clumps or more densely packed clumps, and some of them are more sparsely populated. And so to go along with our collision theory, what would you expect in denser clusters? Well, whenever there's more traffic on the road, you're likely to see more collisions. So in the denser, richer clusters, you see more elliptical and SO galaxies, which are evidence then that those are the remnants of galactic collisions. Because when we go out to the poor clusters where there are fewer galaxies, it's less densely populated, then we do not see as many of those elliptical and SO galaxies. Mostly what we see are the spiral and irregular galaxies, or we at least see more of them. So there have not been as many collisions because there's not as much traffic. And then, of course, there are superclusters beyond just our local group. We are a member of the local supercluster, the Virgo supercluster. So, it's impossible to see everything in the universe, but we are getting a sense of some of the larger scale structure. And it seems that these clusters and superclusters do form in sort of tendrils almost in, that have large voids in between them. And that is basically the shape and scale that we see when we look out. And so finally, let's look at some more bizarre objects that are a little bit difficult to categorize. We have something called Seyfert galaxies, which look like a spiral galaxy, except that the central bulge region is a lot more luminous than you would expect it to be. And the radiation from these galaxies does fluctuate rapidly in how intense it is. We also have an object called a radio galaxies, which emit a lot of energy in the radio part of the spectrum. And then there are the quasi-stellar radio sources, or quasars, which are very luminous and very distant nuclei, or you could think of them as center of galaxies. And so they put out an enormous amount of energy, the equivalent to one supernova going off every hour. And so where is all that energy coming from? It's difficult to say. They're still somewhat mysterious, but it's thought that there is something, well, we know that we think that at the center of galaxies is a black hole, so it would make sense for there to be a black hole here. And so these supermassive black holes, maybe what's happening is that there are magnetic field lines getting twisted around, and then superheated jets are kind of spewing out of the central region. It still doesn't explain everything, but that's really the best guess that we have right now to explain these quasars. And so let's take a look at another subject that we talked about last time, which was dark matter. And you remember that I mentioned that the way stars are rotating around the Milky Way is not how we would expect them to rotate based on how far away they are from the center, and if we assumed that they were rotating similarly to how planets would orbit a star. And so we posited this idea of the missing mass being attributable to something called dark matter. And it turns out that if you look at other galaxies, they have a similar problem, a similar missing mass problem. If you look at how their stars are rotating compared to how far they are out from the center, you see basically the same phenomenon you see in the Milky Way. So this not only is evidence that we weren't just mistaken in our observations of the Milky Way, but that this dark matter, whatever it is, must be everywhere, must be surrounding all galaxies probably, not just the Milky Way. And so when we put dark matter into our theories, then finally we can account for the way the stars actually rotate around the center of galaxies. If we just assume the galaxies are made of stars, it isn't enough to account for it. Even if we add gas in there, it still isn't enough to create the shape we observe when we plot the speed versus distance. So the dark matter is really what we need. And incidentally, clusters of galaxies also gravitationally interact in ways that cannot be explained without the presence of dark matter as well. And so what evidence do we have that this dark matter is real? Well, it can even though we can't see it, it can warp space just like regular matter can and create a phenomenon known as gravitational lensing, which focuses an object that you normally wouldn't be able to see and puts it almost like it looks like a double image of the object to the top and bottom of whatever's creating this lens. And so you see these effects in this image here. So gravitational lensing is taking place, and that is some good evidence that there is dark matter out there. So what is this dark matter? Well, there are two different hypotheses that had initially been proposed for what dark matter would be. Astronomers love acronyms, so there's the WIMP hypothesis and the macho hypothesis. Unfortunately, the macho seems to be losing out here, counterintuitively, I guess you could say. The macho hypothesis basically is saying that, oh, well, this stuff that we can't see, it must be dark planets that aren't giving off radiation, like the Earth even doesn't really give off radiation. Or very old, cold, and dead white stars that we can't see, or neutron stars, or black holes, and all these other various things that don't give off their own radiation. But even if you try and account for it with those objects, it's very unlikely that you could really realistically account for, not even a quarter of the mass that we're looking for, more like 10% maybe if you're lucky. So there must be something else. And so the favored hypothesis right now is the WIMP hypothesis, which is basically that there's some kind of exotic particle out there that is described by particle physics. We can't really go into it in great detail, but that we just have not yet detected.